And it's Friday, and it says vector valued functions, but what I'm really going to talk about is how we can switch from parametrics to polar. It's related. So here we go. So Friday the 9th, right? Yeah. Okay. Kindly consider the following. Here we go. What if, well, you should remember this from September. We talked about polar mode in September. Let's see if we remember this stuff. Here's, where's the circle? Oh, it's right there. Ding. Okay, here's a little circle. And let's say I put a little coordinate system on here. Pretend that's the center of the circle right here. Okay? So where you have the x-axis and the y-axis, and you have an origin, okay? And then you have points along the circle here, right? Well, let's say we take a look at one of those points, like here, okay? You could represent that point in terms of x and y, right? But you could also represent that point with respect to how far it is from the origin, sort of like a vector. How far it is from the origin and the angle that it makes with the horizontal. So let's call that r and theta. So if you think of this as a vector, you can represent the vector in Cartesian or parametric form in terms of x and y, or in polar form in terms of r and theta. You still can represent the same vector. It has a magnitude, it has a direction, all that kind of stuff, right? All right, so what's the relationship between x, y, r, and theta? Is there such a thing? If I draw this right triangle here, this piece here, this is x, right? And this piece here, this is the y value. So, is there a relationship between, I don't know, r, theta, and x? Cosine, right? The cosine of theta is the adjacent over the hypotenuse. Or, in other words, x equals r cosine theta. Does this look familiar? We used to talk about this a lot when we did polar mode at the beginning of the year. All right, how about r, theta, and y? That would be sine, right, okay. So the sine of theta is the opposite over the hypotenuse, which is y over r, or if you want to get y alone, that's y equals r sine theta. Is there a relationship between x, y, and r? X squared plus y squared equals r squared. Okay, good. So if I'm given r and theta, I can convert to x. If I'm given r and theta, I can convert to y if I need to. If I'm given x and y, I can convert to r. Exactly. How do I convert to theta? All right, so in other words, we know r. Here it is. So I could rewrite this statement. I could say, okay, that's x over r. This is r squared, so what's r? So x squared plus y squared in a square root. So if I know x and y, how do I get theta? Arc cosine, right? Arc cosine. And then same thing over here. This would be y over rad x squared plus y squared. All right, so these are a whole bunch of relationships between x, y, r, and theta. All right, focus on this one for now. What if I said that r is a constant? I don't know, 5. 5. All right, so that means, now what does that mean? I'm just plugging in 5 here, okay? Alrighty, so x of theta is 5 cosine theta, and y of theta is 5 sine theta. I could use parametric mode on the calculator to graph this path. I could use polar mode to graph this path. Okay, if you have x and y as a function of some other parameter, t or theta or whatever, you use parametric mode. But notice this means the same thing. This says that r is a constant, but theta can be anything. In polar mode, you graph r as a function of theta. Very often what happens is you end up with things that you can graph, that you can represent in functional notation in polar mode, but they're not really functions. Okay? Because let's graph this. Let's see what it is. All right, let's go to Hal. Where's Hal? Wake up. Hal, come back. Okay, so get out of here. Go to mode. Go to parametric. We saw one like this the other day. Go into y equals. We're going to clear all this. I should just clear all this completely. You know, I'm going to clear all this. Nah, not right now. Okay. All right, so what was it? 5 cosine theta? 5 cosine theta. All right, but I'm in polar mode. I'm in parametric mode, so I can't use theta. I'm going to use t. That's what's expected in parametric mode. And 5 sine theta. Well, it's brutal out there. All right, and let's see the window. Now, x-min, x-max, y-min, y-max can be changed by hand or by zoom, but this you have to specify. I'm going to start, I like to start, if I'm dealing with theta, with 0 to 2 pi in pi over 24, like we did the other day. All right, graph that, and what do you see? Looks like an ellipse, right? Remember, this is not a square window. Remember the difference between square windows and friendly windows and all that fun stuff? See, I don't like this window. This is zoom. Where's zoom on here? Zoom standard, I think this is, right? If I do zoom 6, I get the same thing, right? Remember, I like zoom 4 because circles look like circles and 45-degree lines look like 45-degree lines. It's not squished. So I'm going to change that. I'm going to say zoom 4. And guess what it really is? It's a circle of radius 5. It goes off the screen because this is only, what, 3 point whatever it is. Okay, so that's a circle of radius 5. But note, what if I change the mode to polar? Well, I didn't enter anything yet. That's from God knows when. I don't know what that is. Stop, go away. No, I don't want to do that. Okay, I'm going to clear this and clear this. All right, what if I say r is just 5? R is a function of theta, and theta can be anything, and r is a constant, and that's all. All right. Now let's see, in the window, notice you can specify theta, and this has got some weird zoom again. I don't know if that's a decent zoom. I'm going to do zoom 4 to make sure. It is zoom 4, okay. And you get the same graph. That's the same graph. So polar mode is really, you know what polar mode is doing? It's actually taking what you put in here, right? And actually graphing this instead. If you change your mode back to parametric mode, it's really graphing that instead. It's putting your r in the cosine t into x of t, and taking your r times the sine of t in y of t, and it's really graphing in parametric mode. There is no such thing as polar mode on the calculator. Okay? All right, so that's really what's going on. Now, that's if your r is a constant. That's if your r's are equal. What if your r's aren't equal? What if you made, I don't know, let's change this one and make it 3. What do you expect to see? That'll be an ellipse, right? Because the range of y is at most, is from what? From -3 to +3 for y's. And for the x's, it'll be from -5 to +5. So the x's still have the same range, but the y's do not. So let's graph that. Remember, I'm still in zoom 4. So the circle became an ellipse, and that really is an ellipse. All right? So the x's are going from -5 to 5, but the y's are going from -3 to 3. All right, but what if it's not a constant? What if this thing here is not a constant? What do you get? Let's throw in some stuff like, I don't know. Let's say, am I in parametrics still? Okay. Okay, I'm going to get away from parametric mode because I realize what I'm doing is I'm going to make r a function. But I'm going to make it the same r. If I can make it the same r, if the r's are the same, then that's polar mode. Okay, so I'm just going to go straight to polar mode, so I don't want to have to type all this stuff all the time. But it's really doing this. Okay, so I'm going to go to polar mode now and stick to that. And instead of having a constant here, let's put in some kind of function. How about the square root of, enter, the square root of 1 plus cosine, let's say, theta. And where's my theta? Now, here, you're expected to use theta, and this theta is over here. You don't have a key for it, really. You have to do, what is it, diamond caret? What'd I do? Oh, yeah. Okay, there you go. Now remember what that means. It goes to parametric mode, and it's going to graph x equals this times cosine, and y equals this times sine. It's really not doing anything. There is no polar mode, really. Okay? All right, and in the same window, that's 0 to 2 pi in pi over 24, and if that's not sufficient, we can change it. That's how you play with your window. And this is a zoom 4, right? So let's see what that looks like. And you get something that's called a cardioid. No. Okay, Patrick, you just made history. It's the first time I had that described thusly. Yes. Okay, hopefully that didn't get on YouTube. Hello, YouTube. All right, so, yeah, we're over 10 minutes, so you're lucky. So that's